Hello, we are group 2 from mechanical engineering, and today we're going to present about battery gate under kix2005. So here are the team members. I am Muhammad Hakim, the project leader. Here are my friends, Gilfred, Aiman Zakwan, Amirul Hakimi, and Zulhilmi. So the table of contents. First, we're going to start off with battery gate case breakdown. Then we're going to sustainability in product design, usage, and disposal. Next, ethical issues from planned obsolescence, then balancing corporate interest and ethical obligations. Section 1, battery gate case breakdown. So, a landmark controversy exposing how Apple secretly throttled iPhone performance and what it revealed about transparency, consumer rights, and corporate accountability. I'm passing on to my friend Zuhilmi for the next slide.
Hi, my name is Muhammad Zulhami bin Mokhtar. So let's look at the timeline of the battery gate incident to understand what happened. First, the problem emerges. So iPhone users start to noticing their phone will suddenly shutting down during the normal uses, even when they still have enough battery percentage left. So next is the hidden update. To fix this, Apple released the new update, which is iOS 10.2.1. So they told the public that it was just for bug fix, but it is secretly slow down the phone processor speed to stop the sudden shutdowns. And then come to the discovery. So the independent investigator did some testing and exposed that Apple really hidden the performance management system. And finally, the fallout. And then Apple had to publicly apologize, and they faced global anger, major lawsuit, and also the million of dollar in fine. So this timeline bring up a big ethical question: was it right for Apple to change how phone performs using a secret software update without telling the customer? So now let's look at the technical reason behind why this happened. So now, why do lithium-ion batteries degrade and get weak over time? From an engineering standpoint, there are three main technical reasons. The first one is the chemical aging. As the lithium-ion battery gets older, their internal resistance naturally goes up, and this means that they lose their ability to give up stable electrical power. And the second reason is the key accelerant. Things like extreme hot or cold temperature and also the draining the battery completely before charging it will make the battery age much faster. And lastly, the protective shutdowns. So when an older battery cannot provide enough voltage during heavy tasks, the phone will shut down automatically to protect their internal parts from getting damaged. To rob this action, Apple technical solution to slow down the phones to prevent shutdowns actually made sense from engineering perspective. However, hiding these facts from the consumer is what made it a major ethical failure. I will now pass the presentation to the next speaker to discuss about the sustainability.
Moving on to section 2, sustainability across the product lifecycle. Mechanical engineers play a crucial role in ensuring sustainability throughout every stage of product lifecycle, from initial design to final disposal. The decision made by engineers directly influence resource consumption, environmental impact, and product longevity. The Apple Batterygate incident is a good example of how early engineering decisions can affect sustainability throughout a product's entire lifespan. In this section, I will discuss sustainability from three perspectives. The first one is product design, second one is product usage, and the third one is product disposal. Alright, first let's look at the sustainability in product design. The design phase is considered the most critical stage because the decision made here determine the material use, energy consumption during manufacturing, product lifespan, and recyclability at the end of life. There are three key engineering principles highlighted in this slide. The first principle is design for disassembly. Engineers should design products so that the important components such as batteries can be easily accessed and be replaced. In the battery gate case, a replaceable battery design could have reduced the need for premature device replacement and extended the product's useful life. The second principle is product longevity. Engineers should optimize battery chemistry and battery management system to maximize the battery cycle life. By extending battery lifespan, product remain functional for longer periods, reducing the frequency of replacement and lowering resource consumption. The third principle is sustainable material selection. Engineers must consider factors such as embodied energy, greenhouse gas emission, and recyclability when selecting material. Choosing recycled and environmentally responsible materials helps minimize environmental impacts throughout the product's life cycle. Next, we have sustainability during product usage and disposal. For sustainable product usage, engineers should provide transparent battery health monitoring system. This system informs the users about battery condition and notify them when replacement is needed, allowing devices to remain operational for longer. In addition, maximizing the operational lifespan of a product reduces the environmental cost per unit of value delivered. Mass and energy balance analysis helps engineers to understand the true environmental costs associated with manufacturing and premature disposal. For product disposal, engineers should follow an end-of-life hierarchy. The preferred sequence is reuse, remanufacture, recycle, reconfigure, disassemble, and landfill only as a last resort. Many smartphone components such as displays, cameras, and processors can still be reused after a device reaches the end of its service life. Valuable material, including aluminum, copper, lithium, cobalt, and rare earth elements, can also be recovered through recycling. Therefore, products should be designed to facilitate easy disassembly and material recovery, helping to reduce waste and conserve valuable resources. Overall, sustainability can only be achieved when engineers consider environmental impacts throughout the entire product lifecycle, from design and usage to final disposal.
So for section 3, we are diving into a critical conflict at the intersection of modern engineering, business strategy, and ethics, which is planned obsolescence. Planned obsolescence is the deliberate design of product with artificially limited lifespan. At its core, this practice forces us to look at a massive compromise in engineering integrity. When we intentionally design hardware or software to fail or become obsolete sooner than necessary, we are directly choosing the corporate profitability over consumer autonomy and also the environmental stewardship. 5 core of ethical concern. The first one, lack of transparency. Apple secretly throttled performance without clear disclosure, which violate the NSPE Code of Ethics. The second one, the violation of consumer right. Consumers felt manipulated and financially disadvantaged as many believed their device were deliberately slowed to force upgrade. The third one, environmental and sustainability harm. So the shorter product lifespan increase e-waste, energy use, and raw material consumption, conflicting with responsible engineering practice. The fourth one, corporate profit versus the engineering duty. As engineer, they must prioritize public welfare and integrity over financial interests, even when the corporate pressure suggests otherwise. For the fifth one, and the last one, erosion of public trust. Hidden limitation damage consumer confidence in engineers and manufacturers. Even though the Apple's subsequent apology and battery health features helped a lot, but their reputational damage was lasting.
Next, for balancing corporate interests and ethical obligations, for the corporate perspective, they're protecting the brand image as premium device maker, preventing negative publicity that could impact sales and investor confidence, and Apple's financial growth continue despite the controversy, demonstrating that there is strong brand dominance. But for the engineering ethics perspective, NSPE Code of Ethics demands honesty, transparency, and prioritization of public welfare. Concealing the throttling features undermine consumer trust and professional accountability. True sustainability requires ethical decision-making, not just technical fixes, and engineers must balance innovation, profitability, and integrity. So, a technically sound solution implemented without transparency is still an ethical failure. So, the key takeaways are: first, transparency is non-negotiable. Any change that affects product's performance must be clearly communicated to consumers at the time of the release. Second, design for the full life cycle. Sustainability must be embedded from design through disposal. Dispersible batteries, recyclable materials, and modular architecture reduce the environmental impact. Third one, ethical balances engineering and business. And lastly, consumer rights must be protected. Planned obsolescence, when hidden, constitutes a violation of consumer rights and professional engineering responsibility.
And here are the references that we used for our report. Thank you for your time to viewing this video and have a good day.